Welcome to Maths with EJD. In this video, I'll be talking about spectral analysis of temperature variations. Since we're still discussing spectral analysis um, case studies, in the last video, we had considered some three case studies. But in the next three videos, I'll be looking at some different case studies that are in all other fields so that we can bring this to a close after these three applications. All right, so talking about spectral analysis of temperature variations, we'll be seeing how to, of course, we already know that spectral analysis is about analyzing data in the frequency domain, bringing data from the time domain to frequency domain. So it basically deals with time series, right? So dealing with spectral analysis of temperature variations will see us taking a particular data set in the time domain to then we pre-process that, and then we take it into the frequency domain. Then we carry out spectral analysis and get things like power spectral density, and then we interpret the results. So the scope and learning outcomes in this case are as follows. First of all, we'll be by the end of this video, we'll be able to curate a temperature time series, whether it's hourly, daily, or monthly, and we justify sampling design and check stationarity. Then we'll build a cleaning plus detrending plus resampling pipeline suitable for spectra, right? I mean, we've done things about detrending, resampling, and all that previously. Then we can estimate the spectra in terms using periodogram, Welsh power spectral density, the Lum's cargo for uneven sampling, and time frequency representations like short-time Fourier transform (STFT). Then we quantify and interpret canonical peaks like diurnal, annual, semi-annual, peaks like that, and compute uncertainty like 95% confidence intervals and report domain credible conclusions, right? So first of all, let's look at the kind of data we need to use for spectral analysis of temperature variations, right? So data and assumptions. First of all, what are the typical sources of data that we can use for if you are dealing with temperature? Of course, depending on your context, especially if you are getting a primary data, right? So you can get temperature data from a local station logger, which records minute by minute or hourly temperature recordings. Then you can also consult the city weather API, right? Maybe like some kind of software where you can get updates. Then you can also get like a teaching file, for maybe for daily or monthly temperatures. Then you can get graded analysis. Uh, these are already averaged to daily and monthly, like that. Then the expected columns in the data set, yeah, you'll be working with should be things like timestamp and temperature. These are like the possible variables we should have. Timestamp, maybe it's if you're taking a daily temperature or hourly temperature or weekly or monthly or whatever you're doing, we get the timestamp. So ISO, UTC or local with clear notes. Then for the temperature, say you can take it in degrees centigrade. Then it is optional. You can check, you can have quality flags if necessary. Then what are the sampling cases in this case? All right, in the case of temperature variations, so it can be hourly, right, which highlights diurnal, that is approximately one cycle per day kind of thing, plus some harmonics. Then you can also go daily. This suppresses diurnal. It emphasizes annual, which is approximately 1 over 365.24 cycles per day, plus semi-annual. All right. Then you can also have monthly sampling cases where you have long time cycles. So this is annual is still visible, but it is coarser in this case. So then we can talk about canonical frequencies like cycles per day, which is CPD. So for annual, it is approximately 1 over 365.2425, which is approximately 0.00277379 cycles per day. For semi-annual, it's approximately 0.005475 cycles per day. For diurnal, the needs will be greater than or equal to hourly data. That's like 1.0 cycles per day. And for semi-diurnal, you have 2.0 cycles per day. So let's look at the pipeline overview and decision flow. Since we are talking about spectral analysis for particularly temperature variations, So first of all, we ingest and do some sanity checks. So you want to pass the timestamps. You want to sort chronologically because, of course, time series should be chronological and it should be uniform. But of course, if it is not uniform, we have things like the I think is that the lump Kaggle or something like that that we use for that. Then you can drop duplicates. You can inspect gaps. So this is some kind of preparation, data preprocessing. Interestingly, we had considered data preprocessing in one of the earlier videos, right? Then you can also harmonize the sample. You want to choose the analysis cadence. Do you want to do, maybe you have a weekly thing and you want to do it daily. So you can do something about that. Or you have a daily stuff and you want to go weekly, monthly, and things like that. You can resample, right? So choose the analysis cadence, e.g. daily, hourly, monthly, weekly, whatever. Then you can also you can do some downsampling. You can apply anti-alias, which is low pass filter before resampling. Then you can also upsample, right? You can upsample. So never create invented high frequency content. Interpolate only for small gaps. Then for quality control, you can remove impossible values, any value that is impossible. So you want to inspect to be sure, like maybe you have some outliers that don't make sense in your data set. So like maybe you're dealing with temperature variations and you have something like 100 degrees centigrade. You can already know that that's almost impossible on Earth, like 100 degrees centigrade. So you have quality control, where you can remove impossible values, apply uh, quality flags, cap outliers with domain-aware thresholds, right? For temperature stuff, right? If you're in a particular place, I mean, if you're in a place like, say, Japan, where I am, so if it's difficult to get any temperature less than minus 10 degrees centigrade. That's even rare. But I mean, that's the lowest temperature ever recorded, I think, minus 10 degrees centigrade. And it gets highest maybe when at the peak of summer, you can maybe get something like 40 degrees, 41 degrees, which is also rare. So if you're saying like 60 degrees for Sendai, of course, something is wrong somewhere, right? So you can talk about missing data strategy also. You can have short gaps where you interpolate. That's time-based, which is maximum allowed window. Then you can also have long gaps, which will leave as not available number and consider lumps Kaggle method because of the missing samples. Then you can demean and detrend. So remove mean and linear trend to reduce low frequency leakage. Optionally, you can apply STL to isolate climatology if focusing on interannual stroke mesoscale signals. Then we talk about spectral estimation. So you want to do even sampling. So like you can use Welsh power spectral density, like you can use Hanning window and overlap. For uneven sampling, you can use the lumps Kaggle method. For non-stationary focus, you can use short-term Fourier transform spectrogram. Then for uncertainty and peak picking, right, you can compute 95% confidence interval via chi-square bounds for Welch. Then you can identify peaks near canonical frequencies, compute peak power and bandwidth. Then for domain interpretation now, so of course, by the time you're all done, you want to be able to interpret in the context of weather and climate, right? So you want to map spectral peaks to physical drivers like annual or diurnal cycles, local microclimate, land sea breeze effects, and topography. Then there are sensitivity checks too you can do. You can vary segment length or window size. You can test with or without the trending. You can check stability of identified peaks. Then you can give a report, right? You can document methods and parameters, include figures, for time series, power spectral density, and spectrogram, provide table of identified peaks, interpret results, and note limitations. All right. So let's go ahead and do a practical guide, which is a step-by-step guide with Python. So here, the libraries to be used to be things like pandas, NumPy, SciPy, Matplotlib, and optionally, we can use stats model for STL. So first of all, we ingest QC and resample. So this is more like data preprocessing, the data preprocessing stage. So first of all, we import the necessary libraries like NumPy, Pandas, SciPy, Matplotlib. So if you don't already have them, you have to first of all install using pip install NumPy, or you can install everything at once. Pip install NumPy, uh, Pandas, SciPy, Matplotlib, like that. Okay, so here now we want to use a data set called temperature.csv. So this is the part now. So this is the data set we want to load. If you click here, you can see that we don't already have the data set here. So we only have the default data set. But before I even open it, let me show you that data set here. It's temperature. It's a comma separated values file, and this is it. So it's it contains the timestamp. Since we expected for spectral analysis, we deal with time series, right? So here now, so you have temperature. I actually made this up, right? I made this up. So you have temperature from 1st of January 2023 up till I think about 150 data points. So up till 30th of May 2023. So we have all the temperature for all this 150 days like that. So that is exactly what I want to upload there into Google Colab. So I come back here and I just come to this upload right here, and then I pick up this temperature full file. Then it tells me ensure that your files are saved elsewhere. This runtime file will be deleted when this runtime is terminated. So make sure you have your file saved somewhere in case you need it later, right? So now I have the document here. So now I can run this one without trouble. Okay. So here now, I have this. I have inquest, QC, resample, import numpy as NP, pandas as PD. Okay, we've talked about all that. Then you load the data set. So to load the data set now, we give it a name, DF. That's technically data frame. So here we are converting a CSV file into a pandas data frame because what we read it with is read underscore CSV, which we get from pandas. That's why we have PD dot read underscore CSV. And then this is the document we are reading. So we expect columns called timestamp and temperature. Then for the timestamp column variable, so we convert. So we have a function in pandas called to underscore date time. So it's better to convert the timestamp. If you look at the way we have when I showed you this the other time, you look at the way we have the timestamp. It's like we have this 1/1/223, and that's how it all goes, right? But when you're analyzing with it using pandas, you want to have it in the date time format like that. So you to see through error scores. Then for some kind of data cleaning, you drop drop not available data. So anything that is not available. Thankfully, in that data set, everything is available. But if something was not available, this will help us to get rid of that. Then the next thing we talk about the basic QC. Maybe I should even do it step by step. Yeah. Okay, let me do it at once. So I don't because I have other codes waiting. So basic QC, drop duplicates and insane values, customize thresholds to your climate, right? Make sure what the data you have for a particular, the location is not specific here, so I just did something random. So in case you have your own location, you want to check the data to be sure nothing goes wrong like that. So in this case, now we're assuming that the temperature should be between -80 and 60, right? In our case. So we do that limitation. Anything outside this range, we know it's out of it. So then you choose analysis cadence. Do you want daily? If the raw data is sub-daily, anti-alias, then downsample. So in this case now, if df.index.inferred underscore frequency is none, infer by passing rounding to nearest minute or hour. Keep assist will resample explicitly, or you can pass it. So what we have there is a daily data set already, so no worries. So then you can do low pass daily aggregation to suppress diagonal aliasing only if data is at least hourly, else skip. So our data is not hourly, it's daily, so we can skip. So this is the code to do all of these things. So if df.index.toSeries you differentiate and you have total seconds, median, this, that's just our way of doing it, like a 12-hour rolling stuff. Else, we just go ahead and read the temperature directly. So here now we now have daily aggregation. So our data is daily, so no worries. So for daily aggregation, if it wasn't daily before, would have had to do this, but it's not necessary because the data is already daily. Then we now say handle missing. So small gaps interpolate, large gaps remain NaN. But here we don't have anything missing. So if I run this now, so you can see the code ran very well. So if you're interested in reading the what if you're interested in reading the data frame, right, I can just come down here and just say df. So if I run it now, it just shows me that data. So it shows us that data frame with the timestamp. So you can see it is no longer // it is now in the timestamp. What is it called now? It is now in this date time format, which is good for analysis in pandas. So here it tells us 150 rows and 2 columns. So we see all these temperature, even after the conversion, this is what we have right here. So you see nothing has changed because there are no missing values per se. All right. So then the next thing we want to do is to demean or detrend. This is done to reduce leakage, right? And the way to do that is So you already see up here that we have daily underscore I is daily dot interpolate, blah, 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 like that. So here now, we just have X is daily I minus daily I mean. So you remove the average from that daily thing, all right? And then you now remove the linear trend. So that's X underscore DT is equal to, so this is the variable name now. That's the PD series. Then you now say signal dot the trend. X now drop not available values and do linear series. So index X drop and then you do the indexing. Then you prepare evenly sampled vectors. You have X underscore DT equals x dot dt as frequency 1 day and first regular daily grid. So the data is already daily, so no worries at all. So we have that. And then we now have fs is this, it's 1.0. So if you like, you can actually, you want to visualize the current value of x now. So if I run this now, so it does what it has to do, and then it shows us the whole, what we have done after removing after the trending, the meaning and the trending. This is now the new value now. So that's like some way of preparing towards other things we need to do. So if you want to focus on interannual variability, first remove the climatological seasonal cycle, like compute day of year mean from a multi-year record and subtract anomaly, then the trend. So we've done what we needed, what we need to do here. So you can see the temperature, we now have some negative values because we have removed, we have demeaned and we have detrended like that. So that helps us to get to remove some unnecessary signals. Now we go ahead for Welch power spectral density for even sampling. So in this case now, we choose segment length and balance resolution versus variance. So we have, and length is x underscore dt, like we've seen. It's actually 150 rows and 1 column in this case because we have detrended. So we now have e.g. 8 per segment if possible. Number per segment now is integer of 2 NP floor, this whole thing like that. So that's at least 128 power of 2. So no overlap n per seg with integer division by 2. So we divide by 2, whatever whole number we get is the answer. Then we use Hanning windowing method, and then we plot the periodogram versus the frequency using all this. We've seen this a couple of times. And we go ahead with the 95% confidence interval for Welsh power spectral density using chi-square, which V is approximately 2k degree of freedom, where k is the number of segments. And then we have our k defined this way: nu alpha ci underscore low, ci underscore high. That's talking about the confidence interval now. We have the low and high, right? 95 degrees, 95% rather. And then we do the plotting here. What we are basically plotting will be the power density. And the power density now is about degree centigrade squared per cycle per day. And then we now have frequency, which is in terms of cycles per day. So we run this now and we see the plot jumping out. So that is that data set that we imported now. So we have the frequency right here, and we have the power density right here for in terms of temperature degree centigrade squared per cycle per day. So, and this is talking about the daily temperature PSD Welch. So the straight line is the Welch power spectral density, while the margin, you can see the margin spreads below and above. It is a 95% confidence interval. I guess this was only possible because did we import Seaborn initially? Okay, Seaborn. Okay, we did not import Seaborn. Interesting. Okay. Oh, okay. All right. So we have for the confidence interval, let me see. We have okay, star.chi.ppf. Okay. Yeah, that works. All right. So this is what we have now. So for the annual 1 over 365.24 cycles per day, we have the line right here. So that's like where we get that's the peak if you're dealing with annual data. If you're dealing with semi-annual, that's 2 over something. So we have the peak around, so the frequency is somewhere around here, like that. So we have all of that. Then what about if we want to identify, we can do peak identification and some metrics with respect to peak identification. All right. So you want to find prominent peaks, like you want to tune prominence to your data scale. So you have peaks, comma props, find peaks, PXS, prominence, blah, blah, peak table. You have you create a data frame to get frequency of cycles per day, that's f of peaks. Periods per day, you have 1 over maximum frequency of the peaks. You have the power, you have the prominence, then you sort the values in descending order, because ascending is false. Then example, extract power near canonical bands. So you can define band power and all this. So with all this necessary, so that's frequency, that's periodogram, that's the harmonic. Yeah, that's the fundamental frequency, I think. That's that which is called the harmonic. You have the width to be 0.25. So yeah, we're integrating power around target frequency F naught over plus or minus with in relative terms of percent. So we have the low high. So this is the low, this is the high right here, minus plus, as you can see. Then you have M defined this way, and all of this will go. Then you have the annual harmonic, you have the semi-annual harmonic, then you have annual power, semi-power, you have all of this. Then at the end of the day, we can run this, and then we get a table telling us all those information. So frequency cycle per day. So we have 0.07812. We have period days, that 128 days. For the power is 714. The prominence is 246. Then if we have 2.32732, blah, blah, we have 0.429 as the frequency cycles per day, and the power is 26.5. The prominence is this, and so on and so forth. Then we can now have the band power analysis. So annual band power is not available, sadly, not available degree centigrade squared. Semi-annual band power not available. Then relative seasonality. So maybe with another data set, the value, I made up the data set, so probably that's why we have this like this. All right. So, but if you have another data set, you may get actual results here. So so take note that a small table of top peaks with frequency, period in days of power and sentence on physical meaning. So that's what the report gives us. So that's the report up there. So uneven sampling. So, now we've done the first thing we did was for even sampling up here using Welsh power spectral density. And then we tried to check some peak identification and metrics, and most of the values were unavailable. But when we got to the band power analysis, then here, if you have uneven sampling, so in this case, you need to use the lumps cargo stuff. So this is used when gaps are large or timestamps are irregular, e.g. missing this. In the data set I provided, there are no missing days. So no, we don't have to worry. But of course, if you run it, it will still be fine. So, we have X of U daily minus daily mean, TU, XU drop, YU, XU drop values, frequency grid suitable for lumps cargo. You have all of this set up here. And then we can just go ahead and run. And we have this. So in our case, we don't really have so much trouble. So that's why. So for the annual, we have the solid line there. And for the semi-annual, we have, then the rest is almost near zero each time. Then we can also talk about time frequency. That's talking about things like short time Fourier transform, which results to spectrogram. So this is useful if you suspect seasonality strength shift over years. So using this whole code, which you can look at properly, we get this kind of spectrogram like that. All right. So we have time, that's days since the start, and then we have the frequency right here. And then talking about the power now, the yellow regions tell us regions of high positive power, and the very dark side tell us the regions of high negative power. So what about the interpretation framework? We see that here we see that for the map spectral features to physics, annual peak 1/365 cycles per day. That seasonal cycle driven by solar geometry, expect dominant power in most climates. Then we have semi-annual, amplification from asymmetric, seasonal transition, spring, autumn, original monsoon patterns. Diurnal, so visible only in sub-daily data, like maybe you're doing data maybe in half a day or hours like that. Amplitude influenced by solar heating, cloud cover, humidity, and land cover. So that's more like more immediate, right? Low frequency continuum represents interannual variability, climate regime, stellar connections, and local urban heat island effects if trend not fully removed. Then we have the quality, strength, and uncertainty like that. So report relative seasonal power. So express annual or semi-annual band contribution as the percentage of total variance. Provide 95% confidence interval, CIs on power spectral density using chi-square bands. Clearly note Welsh settings, segment length, overlap, window. Conduct sensitivity test. Repeat power spectral density with plus or minus 25% change in number per segment. Then compare results with and without the trending. Then assess stability of identified peaks. Now we have typical pitfalls and fixes, right? So aliasing, always apply low pass filter before downsampling, confirm Nyquist criterion. I think we've done a video in this line before to know the number, the Nyquist criterion that whatever you're dealing with should be 2 times highest frequency of interest. Then that's 2 times F max. Then that means that the sampling frequency, Fs, should be greater than or equal to 2 times maximum frequency, F max. Then spectral leakage, the trend signals use Hanning window and prefer Welch over raw periodogram. Over interpolation, avoid filling long gaps for FFT. Use Lomscago for unevenly spaced data. Non-stationarity, complement PSD with STFT. Restrict conclusions to intervals of quasi-stationarity. Then units and scaling, report PSD in percentage degree centigrade squared per cycle per density per day. That's talking about the density and explicitly state units. Then deliverables in this thing we have done. Okay, so okay, I don't think, do we need this? I think we've done this a lot. Yeah, do we really need these? Are just okay, maybe I should just run over this. So things we can easily reproduce using notebook, right? So data ingestion and QC, all of this we've done. Resampling, anti-alias steps, the trend and rationale, PSD Welsh with parameters 95% confidence interval, optional Lomscago, then figures, time series, raw, clean, and the trended. I don't think we need this whole thing. I think we've talked about it already. Yeah, I can as well just let this go, right? So I can just delete this. I don't think we need it. Yeah, because we've talked about it before. So this now becomes like our 23.5. Okay, so this at this point now we're talking about some kind of hourly variant. So if you want to talk about some hourly stuff, right? So some key tweaks we can do. So keep hourly cadence. So sampling frequency is now 24 cycles per day because we're now talking about hourly, 24 hours. So add vertical lines at 1.0 cycle per day and 2.0 cycles per day for semi-diurnal. That's semi-diurnal, I think gives the idea of like twice a day, right? So anti-alias before any daily averaging or perform two analysis. Hourly to study diurnal, daily to study seasonal, right? So resample daily data to hourly using linear interpolation. So if that, the data we had is daily. So now we want to make it hourly, right? So we have hourly sampled equals daily resample 1H interpolate method linear. So we say display hourly resampled head. So we run this and the daily data we had before, we just had 1st of January 2023. Now it now becomes like in fact, I think I even want to see, let me remove all this so we can see something more, so we can see more of this. Okay. So now we are going to have like 3577 rows because in one day we have 24 hours. That's like 24 hours times 250 thereabouts. And that's why we have we have this many kind of values. So this has converted the daily data into hourly data. So assuming hourly series hourly, that's degree centigrade with frequency equals H. Using the resampled hourly data, now we can now do some other things here. So following this whole code thing, so we can now draw we can have the Welsh, so we can have the resampled hourly temperature, power spectral density Welsh. And then of course we have the regular Welsh. Then we have the diurnal, that's one at 0.10 cycle per day. That's of course 10 raised per 0 is 1. Then semi-diurnal is somewhere around here. That's 2.0 cycles per day. Like that, we have the power density right here. Okay. So then we can talk about seasonal trend and decomposition and notch. Seasonal trend decomposition and notch. So seasonal trend decomposition, that's STL, to extract a clean seasonal component, analyze power spectral density of residuals to probe subseasonal variability, notch filtering to remove annual peak and inspect nearby bands. Be explicit about filter width and ripple. Okay, so that's what we are doing with this long code. So I just run the code and paid and put paid to this particular video on spectral analysis of temperature variation. So this is pretty lengthy. So you want to go through, extract a clean seasonal component with STL and do all of that. So I'll just go ahead. We are using the same temperature.csv, by the way. So I just run this and then it takes a bit of time and we get some results out here. So this is also the trending and extracting features. So we have the seasonal trend decomposition kind of thing. So original data, that's the blue data there. Then the seasonal data is this one. The trend is just I mean the trend seems to show that there's no trend because it's more like a straight line. All right. Yeah. So we have residual, we have this residual this way, and we have residual PSD with 95% confidence interval. That's before notch. And then we come here, effect of notch. Now, after applying the notch, we now have this. So you see, before notch is blue. So we have this blue thing running in the background somewhere. And we have the after notch, that's the orange color. All right. So, and then we can get some data reading right there. So we have the seasonal trend L and Welch summary. So daily samples is 150, coverage is 100%. STL period 365, seasonal is 13, trend is 367, robust, true. Welch, window handling, number per second 128, number of overlap 64, that 50% overlap because we have 64 out of 128. Annual frequency 0.002738 cycles per day. Then notch, IIR notch, Q is 6.0. So bandwidth is now like 4.53 178 times 10 raised by -5 cycles per day, and it is two-sided. So I mean, if you're working with temperature and you want to do spectral analysis, this gives a kind of background to that, right? I mean, you may need to get more clarity on how you end up explaining your results in terms of temperature. So, but this is a nice background for us. In the next video, I think we'll be talking about machine vibrations, right? Like we'll be talking about vibration analysis, spectral analysis of mechanical vibrations, I believe. That's what that will be about. So with this, we come to the end of this very interesting video about spectral analysis of temperature variations. Let me know how helpful this is, and if there's something you'd like me to try out, feel very free to let me know too. If you have subscribed already, thank you so much. If you haven't, go ahead and subscribe because you have a lot to gain on this channel. Subscribe and don't forget to hit the notification bell so you can always get alerted each time a new video is released. After doing that, you can take it a step further. You can become a member of my channel by clicking on join, and you see different levels of membership, right? And that can give you some extra privileges of being a member of the channel for sure. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Until I come your way again, keep doing maths, data, Python right. Bye.